All right, we're going to look at one more example of a limit at infinity. This will be the limit as x approaches infinity of log of 1 over x. Well, again, composition of functions. So let's examine what's going on. Let's let u equal that 1 over x on the inside there. Let's figure out what that is doing as x approaches infinity. Well, we know as x approaches infinity, 1 over x is approaching 0. In particular, because the graph of 1 over x is like this, as x approaches positive infinity, that would be over here. And we can see 1 over x, the value of this function is going to be coming down from above, right? So it's approaching 0 from the right in particular. So if I do the variable conversion, and I would write this as the limit as u approaches 0 from the right, okay? Our corresponding value of u, of log of u. And now the question is, what is going on with log of u? Well, remember that log of u is a function that looks like this. Okay, if this is our u-axis and this is our y-axis, log of u is a graph that looks like that. And so as u is approaching 0 from the right, as u approaches 0 from the right, our log of u value is heading down towards negative infinity. So the answer to this limit problem is that it's approaching negative infinity. So that's an example of a limit of a function as x approaches infinity that actually ends up being a divergent function. So this doesn't equal a finite value. This is a negative infinite value. So this is not a horizontal asymptote. You only get a horizontal asymptote when your limit at plus or minus infinity equals a finite number. This is just a divergent function. So I have a little bit of space left down here. I thought maybe I would do an example. I'm just going to make up one more example. Since I have some space, might as well do one more here. It occurs to me I haven't really shown you much in the way of examples where x approaches negative infinity, so let's do one of those. Let's do 5 minus x over x squared plus 7. Okay, so given that I just made this up, I'm gonna have to think about this a little bit, but I chose this example for a reason. Let's look at what's happening to the numerator and denominator. Oh, yeah. Okay, so the limit as x approaches negative infinity of 5 minus x, what's going on there? If x is approaching negative infinity, the negative, when you stick it in for x, is going to cancel with the negative there. So this will be more like we're taking 5 and adding large numbers, which is going to be approaching positive infinity. The denominator, x approaches negative infinity, since we're squaring x in the denominator, just because we're approaching large negative numbers, but squaring is going to give us positive numbers again. So this is also positive infinity. So again, we have that indeterminate form, infinity over infinity. So let's apply the same strategy that I showed you last time. So let's take the highest power of x and divide the numerator by that power of x, and divide the denominator by that power of x as well. But do we want the highest power from the numerator or the highest power from the denominator? Generally, the rule of thumb that you can use here is you want to take the highest power from the denominator. So the highest power in the denominator is x squared. So I'm going to multiply by 1 over x squared, 1 over x squared. And then we're going to distribute that multiplication throughout. So boom, boom, and bada-bee boom, like that. I'm going to distribute. Okay, let's see what we get. This is still the limit as x approaches negative infinity, but now our function can be rewritten as 5 over x squared minus x over x squared, and x over x squared will reduce to 1 over x. And then in the denominator, we'll have x squared over x squared, which reduces to 1, and then plus 7 over x squared. Now we can do the thing where we distribute the limit across each and every term. So we're going to do the limit of each of these individually. Okay. And all of the cases where we have a constant divided by a power of x, in those cases, those are all going to approach 0, according to our rule we established earlier. So we'll get 0 minus 0 over 1 plus 0, which overall, this is 0 over 1, which is 0. So this function is approaching 0 as x approaches negative infinity. Sure, that looks pretty good. I just realized that didn't actually work out the way I meant for it to, but that is a fine example, and that'll do. And maybe I'll do one more. Maybe I can do here. I'll do one more for you all, because that was a good example, but it wasn't exactly what I meant to show you. This was an example where the denominator has a higher power than the numerator. Let's look at what happens when it's the other way around. Let's try like x cubed over x plus 5. And I'm going to take the limit as x approaches negative infinity again. I want to do more of this negative infinity to show you what happens. Do I want x cubed or x? Let's do x squared plus 5, yeah. So this time I'm going to approach it the same way, where I'm going to find the highest power of x in the denominator, and I'm going to divide by that. So 1 over x squared again, okay? I'm not going to do x cubed, because if I do x cubed, if I divide by x cubed, then in the denominator, they're all going to approach 0. And that would be a bit of a problem. I don't actually want to get 0 in my denominator. I want to get a constant. So that's why I pick the highest power of x in the denominator and just divide by that. Now, the x's are not going to completely cancel in the numerator. That's okay. That's part of this problem is where the numerator has a higher power, and so we're going to have to deal with that. So x cubed over x squared is x, right? And then in the denominator, we get x squared over x squared, which is 1, and then plus 5 over x squared. So now we'll do the limits. We have the limit as x approaches negative infinity of x divided by the limit as x approaches negative infinity of 1 plus the limit as x approaches negative infinity of 5 over x squared. And this, this is technically, I've done something I shouldn't do here, because the numerator is approaching negative infinity while the denominator is approaching 1, right? So technically this is kind of wrong because that limit doesn't exist. Let me make a note of that. Does not exist. So technically I wasn't supposed to do this, but this does get across the idea, and I think you can figure out from this what the answer should be. Because if our numerator is approaching negative infinity, where our denominator is approaching 1, I think you can see that this answer will, in fact, be negative infinity. Okay. So there's one more example. So that's kind of what I was trying to show you. All of these rational functions can be approached in the same way, where you're approaching them by dividing everything by the highest power of x that occurs in the denominator. And then you should be able to figure it out based on the result after doing that.